Welcome to this explainer. If you're a software engineer, a back-end learner, or honestly just getting your feet wet with system design, you've probably heard the term scalability thrown around a lot. And there's this massive beginner assumption out there that scaling a system just means throwing more hardware at a problem. Like, oh, we got more users. Quick, panic, max out the company credit card and buy a bigger server. But in the world of data-intensive applications, that mindset, it's going to quickly lead to a massive system crash. So today, we are going to completely dismantle that assumption.
Okay, let's dive into this. First, we'll bust the scalability myth. Then, look at describing system load, defining true performance, why averages totally lie to you, strategies for coping with traffic, and finally, workloads and trade-offs.
All right, part one, the scalability myth and rethinking system growth.
So let's break down what we actually mean when we proudly declare that a system needs to scale. I want you to honestly evaluate the systems you're building right now. Is your application actually scalable? Because people love to say things like, oh yeah, my app is scalable, or ugh, that database doesn't scale at all. But scalability isn't just some static label or a neat little badge of honor you can slap onto a project. It's a highly dynamic property.
The actual real-world definition of scalability means actively designing your system so it has concrete, built-in strategies to handle growth. Think about it. If your data volume doubles or your user base multiplies by 10 literally overnight, what are your actual options for coping with that? It's definitely not about mindlessly plugging in more servers. It's about keeping your performance stable while the demands on your system totally explode.
Moving right along to Section 2, Describing System Load, featuring our running example, the restaurant rush. Look, before we can even talk about scaling, we have to know what we're scaling against, right? Think about the journey a user takes on a fast-growing restaurant booking platform during, say, a chaotic Friday night dinner rush. First, they search for nearby restaurants. Well, that's a database query. Then they click on a popular spot to view the menu and some photos. That's a highly repetitive read. And finally, they actually book a table, which changes the available inventory. This creates a really complex mix of read-heavy traffic and write-heavy load. The system is doing a ton of different things, all at the exact same time.
And you absolutely can't just guess how much pressure the system is under. You have to measure it accurately. We do this using specific load metrics, like, is your system struggling because it's suddenly handling 100,000 requests per second? Or is it struggling because of simultaneous active users holding open network connections? Maybe it's the ratio of 1 million menu reads to just one single table booking. You have to succinctly describe your current load using these exact parameters before you can even begin to sketch out a scalable architecture.
Which brings us to Section 3, True Performance, and measuring what actually matters.
Once you know your load parameters, you have to measure what happens when those parameters suddenly spike. So the crucial point here is making sure we don't get our terms mixed up. Engineers constantly use latency and response time interchangeably, but actually scratch that. They are absolutely not the same thing. Response time is what your hungry customer actually experiences on their smartphone. It includes the time it takes for data to travel over the network, wait in line, and be processed. The whole shebang. Latency, on the other hand, is just the duration the request spends sitting, waiting in a queue on your server before it's even handled. All right, Section 4, Why Averages Lie, the Tail Latency Trap. Okay, we've got to bust a major industry myth right now about how we report performance metrics. If your team is only looking at the average response time of your booking app, you are completely flying blind. The arithmetic mean hides extreme delays. A bunch of super fast requests will totally mask the fact that some users are waiting an absolute eternity. Instead, you've got to use percentiles. The median, or the 50th percentile, tells you the exact halfway point of your user experience. But to see the real pain points, we have to look at the 95th and 99th percentiles, often called P95 and P99. That's the slowest 5% and 1% of your traffic. Now, what's really interesting about this slide is how those outliers look when they're visualized. See how most of those individual request bars are pretty fast? That keeps the arithmetic mean suspiciously low. But look at those massive occasional spikes. Your P95 and P99 thresholds are way, way up high. And here is the real kicker. The users hitting those agonizingly slow P99 response times are usually your most valuable customers. In our restaurant app, that slow outlier, it's probably the user booking a massive corporate event with a ton of complex database constraints. If you ignore the outliers, you are literally frustrating your top users. And this builds into a severe architectural bottleneck.
When a user opens a restaurant profile, the app makes several back-end calls all at once, fetching the menu, the reviews, the availability. Notice how it takes just one single slow back-end request to drag down the entire end-user experience. We call this head-of-line blocking. It's kind of like a line at a fast food counter. If the person at the front takes 10 minutes to order, everyone behind them waits, even if they just want a cup of water. One slow component ruins the whole booking experience.
So let's get to Section 5, strategies for coping and adapting to that rush. So our restaurant platform is buckling under those Saturday night traffic spikes. What do we actually do? Well, this brings us to the two fundamental approaches for adding resources. Vertical scaling, or scaling up, simply means buying a much more powerful, way more expensive machine with more RAM and CPU. It's incredibly simple, but eventually you're gonna hit a hard physical limit. Horizontal scaling, or scaling out, means distributing the load across many smaller, cheaper machines. While scaling up is definitely easier to manage, intensive data workloads almost always require scaling out if you want to survive true traffic surges.
And to properly scale out, we use specific architectural tools, applying them exactly where the bottlenecks pop up. For the massive volume of users who are just browsing menus, we use caching, so we don't hammer the database every single time. For the sudden spikes in dinner reservations, we use queues to manage those write-heavy tasks smoothly, completely asynchronously, without crashing the system. As our data grows massively, we use partitioning to split the database into smaller, manageable chunks. And finally, we use replication to keep backup copies of the data across multiple nodes. That way, if one server completely dies, the platform stays online.
Finally, Section 6, workloads and trade-offs, the architecture reality. We've seen the tools, but let's bring this explainer to its conclusion by focusing on the harsh reality of system engineering. Look, a lot of people out there wish there was just a simple, standard checklist they could follow to instantly make their application handle millions of users. But the truth is, there is absolutely no generic magic scaling sauce. An architecture designed to handle 100,000 tiny, lightning-fast requests per second, that looks entirely different from an architecture designed to handle 3 massive, gigabyte-heavy analytical queries per minute. Ultimately, your team must make deliberate trade-offs. You have to design your system based entirely on what you assume will happen most often. Think back to our restaurant app. Reading menus is incredibly common, right? But updating the restaurant's actual street address? Super rare. If you optimize for the wrong access patterns, if your assumptions about your load are just flat out wrong, all the caching and partitioning in the world won't save your system from buckling. So I'm going to leave you with this final thought. Take a really hard look at your own engineering projects today. What are the operations you're assuming will be common? What are the rare ones? Are you measuring the tail latencies of your most valuable users, or are you just hiding behind the arithmetic mean? Figure out your exact load metrics, identify your true bottlenecks, and design a system that actively copes with growth. Thanks so much for joining me on this explainer, and I'll catch you in the next one.